Well, thank you, Manalis. Thank you all for inviting us into this workshop. I'm Josep. I work at Semidynamics, and I will be presenting a little bit what we do in the company and how we are helping into the ecosystem by building IP for the next-gen European cloud. So first of all, let me introduce a little bit the company. Semidynamics was founded in 2016. We are a startup, a company of currently about 150 employees, where our only office is in Barcelona, so we are kind of like full European. And we basically think specialized in optimizing or creating, designing optimized processor, especially for high performance computing, and as well currently now on the AI section of it. So during almost these 10 years that we've been already working, what's our IP that we have been developed, maybe from left to right. We started with a core, with Avispado, and then evolved into Atrevido, where, as Marie said, we develop along with the first API projects, and we continued developing on the subsequent API projects. Along with Atrevido, we've also developed this Gazillion technology that I will talk now. And as well, vector unit, tensor unit, and finally we have integrated everything of these IPs into a NPU that I will present. Well, basically, yeah, I was mentioning the NPU basically is a collection of RISC-V cores, where these RISC-V cores, it's not only the core, but as well vector unit and tensor unit, all of them connected into a coherent NOC, all talking to the same optimized cache that then offers an AXI or CHI bus into it. Let me go a little bit IP by IP, and I will get back into the NPU at later of the presentation. Atrevido, well, it's a 64 RISC-V core, four-way out of order that allows, well, has an AXI or CHI interface into the exterior world. And basically the main concept or the main design of the core is to allow or support long latency memory. So that basically means that although we don't have, or maybe in the data sets that we are working on, taking into account that the Atrevido is hooked up into a tensor unit and a vector unit, which operates in data that is very large. So basically this data won't fit on the L1 cache, probably not on the L2, and you will need to go fetch that data into the DDR. So basically, this is the main concept of design of the core, is to be able to support this very late latency and do it well, so we can keep the data coming in order for the matrix multiplications be processed on the tensor unit or the vector unit. So basically, this is what the Gazillion misses do, is a technology that allows to support a high memory bandwidth, even when this data comes from the other side of the chip. And here I have a diagram where we compare between our core and the Intel i5. Well, basically, as we can see, they do better on the L1 cache, but basically, we don't think that our data will be able to fit on that small storage. So we don't optimize for that. So that's why, for example, we don't have a 2-port or 3-port load store unit, but rather we have focused on being able to bring data from other levels of the memory hierarchy, like the L2 or L3, very well. So basically, we already do better on the L2 and of course L3 and DDR than the Intel, having this thing on as a design principle. Talk on the vector unit is the second IP that we designed. Basically, well, it's a RISC-V vector extension 1.0, allows, as the rest of the core, an out-of-order execution. It supports from 64 to int8, as well the floating point as data types. We also adopted bfloat 16, as we've seen that some of the benchmarks on the AI are being used as well. And the configurations of the vector unit, well, it depends on how big is the vector length, so how large is our vector. as well on how many iterations we do the operation, whether it's in 4 iterations in order to compute the whole vector, or 2, 1. It really depends. I have a diagram of the vector unit here. Basically, it's composed of different lanes that allow you to define the vector register, the size of the vector register, and as well, and how many iterations are needed on this, or how many passes of this vector register are needed in order to compute the whole vector. And finally, the last IP that we've developed is the tensor unit as well. We have started with the IME implementation based on RISC-V. Also, we are working on the AME, which basically the difference is that this IME uses the vector registers as a tensor register. So both vector and tensor make use of the same registers in order to store and get the data from. The AME that is currently being developed makes use of an external or an SRAM or dedicated registers that are not shared with the vector unit. Along with that, basically, this tensor unit brings is very, I would say, very silly IP, but powerful nevertheless. It basically does one operation, which is matrix multiplication, which is the main operation on the AI, and also allows, we have put some loads, taking as a reference the ones that appear on the vector register, basically to bring, to specialize them to bring a part of the matrix. I have a diagram as well for you for the tensor unit. Basically, instead of vector lanes, we have in this case tensor cores, which basically does the operation you see on the right side, which is A times B plus C, and stores the results on the C back to the C register. So with all of these IPs that I've been talking about, we have built what we call SiPearl, which is an NPU, the collection of these three IPs, which is basically the main principles is that it's easy to program. Basically, everything is under RISC-V ISA, the RISC-V core. So you don't need specialized instructions. You don't need specialized compilers. Everything relates to the same ISA. High performance, as everything has built together. Everything is hooked together closely without any external interfaces. As well, this means zero latency, better PPA, because, well, you don't need to integrate into the SoC different chips from different vendors. And, well, it's resilient to the new AI because although you know now and currently have knowledge on what is the current trend on AI, on the next generations, probably it will change. But thanks to the vector unit, which is it's kind of a general purpose GPU where you can implement whatever new operators are needed, and always you will have the tensor unit to provide you with a powerful matrix multiplication. So we offer, well, the survey, it depends on how many cores and how many all-in-ones are integrated. It delivers different performance on it. And not only that, not only on the IP of the hardware side, we also been developing some software, some specialized, well, although we rely on GCC, we are being able to specialize a little bit the GCC in order to fit well on our architecture. And in terms of the AI, we have taken the ONNX, which is one of the runtimes on the AI libraries, and we have adapted, we have implemented and optimized some of their operators, and the operators needed to run the machine learning benchmarks and models in order to run well and run efficient on our IPs, especially on the NPU. And basically, well, we currently have developed or supported all of these models. Basically, any model that you can get from the Hugging Face you can run it through the NX onto our NPU. So thank you for the presentation. I don't know if there are any questions.
I would like to ask a question on slide 9. You had the different matrices and their data types, and you also have one for C. We see that for A and B, you have a very small data type, so integer 4 near the end, but still the matrix, the final result is still 32 bits wide. Is this to maintain essentially a standard length, or is there another reason for this?
Not an expert on the tensor unit, sorry, but probably yes, to have a unified data type. So I think is that all other data types can be converted easily to the 32-bit counterpart, and also to store then the matrix the result into the back to memory.
Okay, perfect. Thank you.
Thank you, Josep, for your presentation. We do have some time in the end of the session if there is any further questions there.